what we're going to do is I'm going to go through the 2019 FRQ, kind of walking through the answers to expound more from the answer document, focusing on the questions that particularly you guys put that you needed more guidance, and then we'll address certain topics as well as we go through it. So let's start with question number 1. Okay, so question number 1, A, says, it gives us this structure right here for this compound urea, and it says to identify the hybridization. And I know that was one thing a lot of you said you needed to review on. So let's just do an overview of how you identify hybridization. So we're trying to identify hybridization of carbon. So hybridization in general, once again, you're not really going to have to explain it ever. You're just going to have to identify what it is. It's based on the idea that when things bond, if the orbitals aren't at the same energy level, such as an S and a P, they morph into these special type of orbitals. So it's not an S, it's not a P, it's an SP, or it's an SP2 or SP3. So those are the only 3 options for hybridization. Side note, I would recommend, as I go through this video, that you take notes on any of those topics that you said you needed more help on, once again, to kind of help ingrain it into the brain. Okay, so hybridization is either SP, SP2, or SP3. Those are the only 3 options. Outside of that, it's all hypothetical at this point. Scientists don't know if they actually exist. So those are 3 options. Now, the way to identify the type of hybridization is you do it by looking at how many things are bonded to that central atom you're focused on. So in our case for carbon, if we look up here, carbon has, or I guess maybe not how many things it's bonded to, but how many domains it has. So it would be 1, 2, and then the double bond counts as only 1 domain. So carbon has 3 domains around it. And so those 3 domains, so now think of 3 in that it has to add up to 3 letters. So that's why it's 1 S and 2 P's to get to the 3. Okay, I'll do another one just to kind of reaffirm. Let's say if this problem would have said for nitrogen, okay, and the nitrogens here are identical, so it wouldn't really matter. Okay, so for nitrogen, it has 1, 2, 3, 4 domains, so a lone pair counts as a domain. So that means its hybridization would be an SP3, because 1 S and 3 P's equals our 4 domains. And that's pretty much it for hybridization. Okay? Okay, question number 2 is about hydrogen bonding. And it wants you just to draw using a dashed line where hydrogen bonding can occur. So the thing to remember with hydrogen bonding in general is that, so for hydrogen bonding, you need an N-O-F sandwich. Okay, meaning the H is in the middle, and on both sides of the H is an N-O or an F. Okay, so one place where this could happen, I'm going to draw in, so this is an N, that's an N, and then all of our clear ones are O's, the dark one is the C. So you could have drawn it here, so here's my H. So here's your O-H-N sandwich, so that would work. It looks like you could have also done one here. You only had to do one, but just kind of showing you all the possible locations. Looks like technically we could have had, because NH, here's another one. And this one's a little weird, but technically there is also one right there as well. Because once again, NO to NH to O, NH to O. So once again, make sure you just look for that NOF sandwich. Yeah, okay, there's hydrogen bonding. Okay, question C, or part C, says, so it gives us this information. Now, once again, in general, with these FRQ questions, Pay attention to the information they give you, particularly when they give you new information within a problem. So in the original question, it gave you information, you then answered A and B. It then gave you this new information before giving you C, D, E. That's a good hint or pattern to look for, in that this new information right here is going to be used to answer the following questions. You may have to use the original information as well, but don't not look over that because it's going to be important. So it tells us here that the dissolution of urea is represented by the equation above. I forgot to put it on this problem, but it's on your paper. It says the student determines that 5.39 grams of urea can be dissolved in water to make 5 milliliters of a saturated solution at 20 degrees. And it wants us to calculate the concentration of urea in moles per liter of the saturated solution. So once again, whenever a problem gives me units, that's just what I focus on. Say, all right, I need moles and I need liters. So in this problem, it says it gives me grams. So I know how we can always take grams to moles. Okay, so we have 5.39 grams. And they actually give us the molar mass already. 60.06 grams to 1 mole. Okay, so once again, I'm just focused on, okay, I need to find moles. So I'm finding that first here. Okay, I plugged that into my calculator and I got 0.0897. Now, once again, for those of you that kind of ask the question, like, how do I know, like, where to go or what to do? It's all about units. So since I'm trying to find moles, I'm focused on getting moles. Okay, I have moles. Now the other unit I need is I need liters. So I go back to the given information and I see, well, they give me milliliters. So I can take milliliters and change that into liters. Right, so it'll be 0.005 of a liter. And then to find the concentration, it's bringing them together. So 0.0897 over 0.005 equals, plug that into my calculator and you get the 17.9 M. Okay, now for those of you that asked about sig figs, once again, I would not stress sig figs, and especially with the way they've shortened the test, I guess I don't know for sure, but I highly doubt that's going to be something they choose to do points on, because I think they're going to care more about the topics they're testing you on than the sig figs. But I always just go back to the given information, and so the given information has 1, 2, 3, 1, 2, 3, and so my answer only gets 1, 2, 3 sig figs. Okay? Okay, there's part C. Okay, part D. Okay, once again, I put that given information because it's a key component in answering this question, and if you ignore it, it can be actually quite confusing of what to do or where to go. So they say that the student determines that the concentration of urea in a saturated solution at 25 degrees is now 19.8. So the first thing you need to identify here is that the temperature went up because in part C it was at 20. So we have a higher temperature and we have a higher concentration. Okay, based on this information, is the solution or dissolution of urea endothermic or exothermic? And then justify your answer in terms of Le Chatelier's principle. Once again, there's a hint here. They're telling you kind of what to look at. So I'm going to write our equation down here just so I can talk about it easier. Whoops. Too many C's. So Le Chatelier's principle is the idea of how when you do something to a system at equilibrium, it will shift to balance it out. And that's the idea of the answer key and talking about the stress. So we were told that we have a higher concentration, which means more soluble. Okay, which means since it was more soluble, that means we have more of our aqueous side, because that's solubility. So that means our reaction has shifted to the product side. Now, the only way for it to shift this way, because we're looking if it's endo or ex, so that means we're seeing is the heat like a reactant or is the heat like a product. So since when we raised the temperature, it forced it this way, that must mean that the heat is on this side of the reaction, meaning it's endothermic, because heat as a reactant is endothermic. Because if it's over here and you add heat, it will shift it this way, causing more of it to dissolve. If the results were opposite, so let's say if the problem would have at a lower temperature, we got a higher concentration, then it would have been exothermic, because that means it would have shifted it the other way. So there is that one. Let me check and see if there are any specific other questions. Okay, so kind of big takeaways outside of this problem. Remember, endothermic means heat is reactant, exothermic means heat or reactant, and then making sure you understand that idea of the shift with Le Chatelier's. I guess some other takeaways that you need to understand is how the higher concentration means it's more soluble, meaning you have more aqueous solution versus the solid. Okay? Okay, let's take a look at E here. All right, so they say the equipment shown above is provided that the student can determine the value of the molar heat of solution for urea. Knowing that the specific heat of the solution is that, list the specific measurements required for the experiment. Okay, so the thing I would focus on here, a lot of you were like, well, I don't even know where to start on this, is what we're trying to find. So the thing we're trying to find is the molar heat of solution, which is joules per mole Kelvin. So these are the units for the molar heat of solution. Technically now with the formula of the test, if you didn't know that, you could just look it up. But it is always that as well. The other hint as well is you should have, which I think a lot of you saw, seeing that they're giving you a styrofoam cup, your brain should have said, okay, we're doing a calorimetry experiment. Okay, now anytime you're dealing with calorimetry or dealing with finding joules, the equation that we're going to use is Q equals MC delta T. So then what I would say is, okay, in a lab setting, to solve for this equation, what information do I need? Well, M is mass, so we need the mass. That's why we need the mass of the urea and the mass of the water, okay, because you have to have the mass of the total system. So that's going to be the urea plus the water. Okay, C is the specific heat, which is given, and then we're going to need the change in temperature, which is final minus initial. So those are the 4 pieces of lab info we need to solve this, which then gives us joules to get us the molar heat of solution. Okay, so in these types of problems where and once again, you can see it in a different way or a different experiment, but take the same approach where I say, okay, what are the units of the thing I'm trying to solve, and what measurements link to those units? Okay, there's question 1. Okay, let's talk question 2 of the 2019. Okay, all right, so here is how it starts. It says, answer the following questions related to the chemistry of halogens. Question A says, the molecular formulas of diatomic bromine, chlorine, fluorine, iodine are written below. Circle the formula of the molecule that has the longest, I'm going to move that down a little bit just so it's not right on that line, even though I know you have it on your own paper. The longest bond length. Okay, now once again, as you're taking the test, I guess it'll be a little bit different because it's on the computer, but don't be afraid and try to make notes of what's given. Pull that information out so you know, okay, what is it I'm trying to find, so you can start directing your brain on where to go. I know quite a few of you, that's the thing you're asking is, sometimes I just don't even know where to go, where to start, or how did I know to go that direction? And the way to know which direction to go is try focus on what we're trying to find. Now, bond length, by definition, is the distance between when these two things are bonded. So the first thing you should look at when you're dealing with bond length, this is in general, is how many bonds are there? Is it a double? Is it a single? Is it a triple? Now, being that these are all in the halogen family, you should be able to identify really quickly that they're all just a single bond. You don't have to draw these out, obviously. I'm just drawing it just to prove a point. But the question would be quite different if it was saying comparing oxygen and fluorine, because oxygen is a double bond, and let's say if we brought nitrogen into it, nitrogen is a triple bond. Okay? All right, the next thing is justifying or figuring out which one's going to be the longest. Side note, by the way, a triple bond is going to be shorter than a double bond. A double bond is going to be shorter than a single bond when you're comparing that way. In this case, because we're looking up and down, that's kind of a hint that you want to know your trends. Now, once again, you're going to have your notes available to you, so it's not just having the trends memorized, or you don't really need to even have them memorized anymore, as it is just understanding how they work. And so, because these are all a single bond, the thing that's going to make the bond longer is the size of the molecules, because of the overlap that they're able to have. So since iodine is the largest of the family, because it gets bigger as you go down the periodic table, it's going to have the biggest bond length. Okay? Okay, question B. Now this one, I apologize for this. You don't need to know how to do actually. This concerns Unit 9. So I'm actually really intrigued for those of you that got it right. And what logic you used to do, so you don't have to worry about it. But I was just interested that some of you got it right and that some of you said you understood how to do it, because we haven't talked about this and you don't need to know how to do it. The only part of this we have talked about is we have introduced what oxidation, what reduction is. Oh, but that's not even in here, it's just an answer part. So if you don't understand 2B, you're fine. Don't worry about it. Let's move on to C. Okay, C says that Br2 and Cr2 can react to form this compound BrCl. Okay, the boiling point of Br2 is 332, whereas the boiling point of BrCl is 278. Explain this difference in boiling point in terms of, once again, they're giving you a hint of where your brain should start thinking, present between, and they even underline it, each of the substances. So my first thought process in solving this problem would be like, all right, well, what forces do they have? So let's review intermolecular forces. Okay, so we have Br2 and we have BrCl. Okay, so we have three main types of intermolecular forces. We have London dispersion force, which everything has. So we know that this one has London and this one has London, because everything has a London dispersion force. It's that momentary shift of the electrons, and since all molecules have electrons, they all have a London dispersion force. Okay, the next type of force that we've talked about is a dipole-dipole force. A dipole-dipole force exists when a molecule is polar, meaning the electrons are permanently shifted one way, not just the momentary electron flow back and forth. So since it's Br to Cl and they have different electronegativities, this one would also have dipole-dipole forces. Okay, this one would not, because it's bonded to itself, so the tug of war is equal. And then the last type of force is hydrogen bonding, which neither of these have, obviously because they don't have a hydrogen, and we reviewed those ones in question 1, meaning they have to have an NO or an F. Okay? All right, so the first thing, that's what I would do, right? And kind of in my scratch work, identify these forces. Then we're trying to link these forces to their boiling points. So the information they give us is that Br2 is at 332 and BrCl is at 278. Now, this is always a true fact. The higher the boiling point equals stronger forces, because that's what's causing it to be higher, is that it's being held together tighter. So what we need to understand here is that this has stronger forces than this, based on the data. Now you wouldn't know that based without the data, because generally dipole is stronger than just a London. But given the data, we have to justify it based on what the data is showing. And so this is a case where the London forces of the BR2 are stronger than the dipole and London forces of the BRCL. Once again, key thing of paying attention to the question and the guidance they're giving you and how to answer it. That's how you can maximize your point value. So there you go. That's how that one works, and kind of a review on intermolecular forces. Okay. All right. D. Okay, now once again, notice I've clipped the information from the question because it probably plays a key role in it. So gives us this information here, and then it says calculate the pressure in the container before equilibrium is established. Okay, so I'm trying to find pressure. I would say 90% of the time when a question says pressure, I would say let's see if perv nert will work. Okay, so if I rearrange perv nert for just pressure, and the way you know if it's going to work is, do you have the information you need? So do I have moles? Yep. Do I have R? Yep, because that's a constant. Do I have a temperature? Yep. And do I have a volume? Yep. And so that's how I can find it. So for those of you that were kind of asking, like, how do I know what equation to use? Anytime a question says find pressure, that's the first place my brain goes, because once again, 90% of the time, that's how you're going to find it, is through the use of perv nert. Plug it in, make sure you do your units right, and that's how you get the answer. Okay, all right, C just wants the expression. Okay, that word expression is a key thing to recognize, because expression just means the setup. You're not solving for anything yet. Okay, so keep in mind, and this is also on your formula sheet, all of our K's are equilibriums, our products over reactants. You could do it pressure-based or concentration-based. Okay, but products over reactants, and then coefficients become powers. So the 2 in front gets put up there. Okay, the key thing there with recognizing expressions. Let me check and make sure there weren't any other specific questions on that one from you guys. Nope, I think most of you were pretty good. Okay, all right, next one. Oh, same theme. Oh, nope, go to the next one. There we go. Okay, so after the system has reached equilibrium, once again, key wording there. After the system has reached equilibrium, 42% of the original BRCL has decomposed. Determine the value of KEQ. So the first one was the expression. Now we have to find the value. To find the value of an equilibrium expression or an equilibrium constant, you're most likely going to do a Rice chart. Okay, so let's get our equation up here again. Okay, because in order to plug values into K, so the K we wrote before, right, was BR2, CL2 over BRCL squared. Okay, these values have to be at equilibrium, not initially, but at equilibrium. And so when we get to equilibrium, that's how we know a Rice chart comes into play. Okay, now there's two approaches you can actually take to this. You can either solve it through pressure or through concentration, and it doesn't actually matter. As long as you show your process, you would get the points for it. Another question some of you asked was like, with rice charts, how do I know when I need an X versus not an X? When you're solving for K, you're gonna need an X value. We'll back up, let me rephrase that. When you're, okay, let me put this in and then I'll say it in a better way. That was not a good way of saying it. Okay, so I'm gonna do mine through pressure route because it gives me the initial, or I found the initial pressure in part D when we use Pertnert. So I know the initial pressure of the system is this. Okay, then the way I would think about it is what they're telling me is they're telling me that 42% of the original BRCL sample has decomposed. And so I know that if I know how much of it is going away, or in a sense how much is left. So 42% of the original has decomposed. So 42% of this. So if I take 1.22 and times it by 4.42, because that would be, tell me 42% of that. I get 0.5124. So I know that this is going away by that much. Now, those ones, the change is always based off the ratio. So it's a 2-to-1 ratio, so I'm going to divide that in half. So 2.562. Okay, like so. Carry it down, so we get 0.26, just rounding here. Okay, and then if I do that one, I get 0.71. Like so. Okay, so so they used X's in their example. I just this makes more sense to me of just finding the change, because we can, and plugging it in rather than using X's to find the change. So generally speaking, if you're solving for K, you won't need X's. If you have a K and you're finding something else, then you'll use the X's. Honestly, the other way around is actually more common with acids and bases, which is now not on this year's test. So I would say, generally speaking, don't think of using X's with rice charts. Because yeah, you won't really use them. Okay, and then we just take these values, plug them in, and that's how you get your K value. And looks like there's one more in this problem. Okay, let me bring that down again. All right, this one wants us to find the bond energy of the Br to Cl bond. Okay, so when you're dealing with bonds, the equation for bond, and this one's not on your formula sheet, maybe since you can use a formula sheet now, it might not be a bad idea to add other formulas to that formula sheet so you have a quick reference when you're taking the test, so you're not just flipping through your notes. So this would be one I would add on there. So bond enthalpy is calculated, is bonds broken. So you add up all the bonds that get broken and subtract the bonds that are formed. Okay, so for our equation, we have 2 BRCLs turning into Br2 and Cl2. So you need to identify how many of each of the bonds there are. Okay, so we have 2 of the Br to Cl bonds, and then 1 Br bond, Br to Br, and 1 Cl to Cl. And then it tells us the overall. So this, I guess, equals delta H. Okay, so plug in what we know. So it's bonds broken. So the ones that get broken are the reactants, because they're reacting and breaking apart. So 2 of those. Now I don't know that value, so I'm just going to plug in that. say, so 2 BrCl bonds minus a Br to Br bond plus a Cl to Cl bond, this bond's formed, equals 1.6. And then at that point, then you just do your algebra to solve for what we don't know, which is this bond. So we combine those, add it over, divide by 2. Okay, there you go. All right, let me check if there's any other. I know a lot of the main questions were on 2B, so that's good, and then on rice chart practice as well. So, okay, there is question 2. Okay, let's talk question 3. Okay, so question 3 gives us this information. Man, I'm really bad at getting it right on the line every time. Okay, so it says student is given 50 milliliters of solution of an unknown concentration. To determine the concentration, the student mixes it with an excess 1 molar solution, causing a precipitant to form. The balanced equation for the reaction is shown below. Part A says, write the net ionic equation for the reaction. So a net ionic equation reviewing is we're going to remove the spectators, things that are not involved in actually making something, meaning they just are ionized in the solution before and after. So I'm going to show you a between step to help those that are missing the understanding of net ionic equations, but you can really just go from this to the net if you want. So when something is aqueous, that actually means, I guess let me back up. When something is aqueous and it's an ionic substance, which these are, it actually exists like this, where you have Na, and you would have 2 of them, and you would have carbonates separate from each other. So this isn't how it is in the beaker, it's actually like this. And then same thing here, you'd have calcium and then 2 nitrates floating around. So things that are aqueous and ionic separate. Okay, so on the product side, we have 2 NAs, 2 NO3s, and then the precipitant, the solids, they do stay together because they are insoluble. So if you look at the equation, that's written this way, but if you look at it this way, what we can see here is that the sodium isn't doing anything in this reaction because it's floating around here, it's floating around there, no difference. And then the nitrate as well, same thing. And so the net ionic equation is only those components that make up the precipitant. And that's it. Okay. Yeah. Check and see if there are any specific questions. Okay, all right. Let's go to part B. Okay, so part B says, so I just gave our information up there again. It says the diagram below is incomplete. Draw the species needed. Actually, I'm going to leave that there. Okay, to accurately represent the major species remaining in the solution after the reaction has been completed. Now, if you look at your net ionic equation, okay, so we see that these 2 things are forming the precipitant, which is down here. You always should have spectators floating around because they're just spectating. And then because they're telling you it's incomplete, go back to the given information. And there's a keyword up there that helps you know what's missing. It tells you that they are adding an excess calcium nitrate. So excess means you are adding more of it than what you need to precipitate. So since you have an excess of calcium nitrate, the thing that's missing in our picture is the calcium. It's also why you have more nitrates floating around. Notice there's 4 of those compared to the 2 sodiums because there's more of it. So that's the piece that's missing. Okay, let's go to part C. Okay, so this one now says the student filters and dries the precipitant. Now when a problem is talking about like they're doing a lab experiment and you're answering questions about it, try to visualize what's happening, make it real, because then it simplifies what is going on rather than just trying to memorize, oh, do this, then do this, do then that. Okay, so filtering and precipitant, remember that goes back to our lab that we did when we mixed two clear substances and something cloudy would appear. That was the formation of a precipitant. So the way you can get a precipitant out, because it's a solid, is by sending it through a piece of paper. The liquid goes through and we catch the powder inside. Okay, so what they're telling you here is that this was the volume of our solution to begin with. We poured these two together, and then this is how much precipitant we got out. So it says determine the moles of sodium nitrate in the original. Now, whenever you're dealing with a precipitant-based problem, the amount of precipitant is key because that is, in a sense, determined through the limiting reactant. We don't want to use the information at the beginning because that was an excess amount. So, if we take that 0.93 grams of calcium carbonate and think, all right, well, I want to get to sodium carbonate. Okay, well, we know those two are related through the balanced equation, which was 1-to-1, I think. Yeah, so in order to relate this to this, the thing that connects two different things is moles. So the first step is we have to go from grams to mole of calcium carbonate. And then we can go from moles to moles. So this is 1-to-1. This would be whatever the molar mass of calcium carbonate is. And then solve it through and we get our final answer. Okay? Once again, this is what we want to use as our starting point, not the 1 molarity that the problem gave in the beginning because that was an excess amount, so that would give us more than what we actually have. Okay, let's take a look at D. All right, so D says the student realizes, let me erase this first, that the precipitant is not completely dried, meaning that this is actually precipitant plus some water. Okay, and claims that as a result, the calculated molarity is too low. Do you agree with the student's claim and then justify your answer? So since this is precipitant plus the water, that means this value is too high. And if this value is too high, thinking back to what we did on C, because C is how we find moles of this, okay? If that's too high, then the molarity or the moles are going to be too high. Okay, they're going to be higher than they should be, and so then the calculated molarity would also be too high. So that's why you should disagree with the claim. So when you're, once again, this is a common thing they like to do on the AP test questions is to talk about like error analysis in the lab. So like if this goes wrong, how's that going to affect your results? And so what you have to do is link back, okay, what is this? What direction is it? In this case, it's too high, and then connect it to the calculation. Normally it's connected to the one you just did. So think about how this affects the answer to C, to know to agree or disagree. So, okay, E says, whoops. After the precipitant forms and is filtered, the liquid is passed through the filter and is tested to see if it can conduct electricity, and then what would be observed, and then justify your answer. Okay, so if we're looking to conduct electricity in a solution, you need free-floating ions, which are spectators, do the job, because ions mean charges, and so that's why the answer is yes, it would conduct. If you didn't have charges floating around, then something wouldn't conduct electricity. That's why sugar water doesn't conduct electricity, or pure distilled water doesn't conduct electricity. It's because you don't have those free-floating ions in there, okay? Okay, all right, so on this one with E, F, or whatever, we're on E. So for F, G, and H, I think it goes to, or F and G, and H. Oh, I actually took H off. F and G, I put them on there originally because they deal with Unit 8, but now that Unit 8 is not part of it, you do not need to know how to do F and G. So if you had questions on those, I hate to do this because I don't want to leave questions, but being that we're focused on for that test, I'd say put those questions aside for now, and we can still talk about it after the test for sure, if you want help with those. But since it's not going to be on there, I'd say let's not focus on it for now. Okay, so there is question 3. All right, let's go ahead and talk question 4. Okay, so question 4 says, student is doing an experiment with carbon dioxide, originally a sample of gases in a rigid container at 299 Kelvin and 0.78 TM. The student increases the temperature of CO2 in the container to 425. Okay, first off it says, describe the effect of raising the temperature on the motion of CO2 molecules. I think most of you actually got this correct, and said you understood it, but the basic idea here is understanding what temperature is, and that temperature is a measure of the speed of the molecules. And so if you raise temperature, you increase the speed. One of you pointed out, kind of asking a little bit about kinetic energy versus speed. They aren't the same thing, but raising the temperature would also raise the kinetic energy. So if you were to say that the kinetic energy of the molecules would increase, I would assume that it would also give it to you as well. But I guess maybe the key word here is motion, and speed refers more to motion than energy does. But they are directly related. They're not the same thing, but they are directly related. Okay? All right, part B, calculate the pressure of CO2 in the container. Now, before I said when a problem says pressure, think PervNerd, which we are using PervNerd here. But if you try to write it out, you'll find that we're missing information. Because if you go up to what's given, the things that are given is they give me a temperature, 299 Kelvin. They give me a pressure already. And then the problem wants us to find the pressure at a new temperature. Okay, so that's how I know PervNerd won't work. It's not bad to think of it at first, but if you're missing information, then it's not the way to go. The way we are using PervNerd here is you can use PervNerd to calculate changes. So if I start at this temperature and then I go to this temperature, how is it going to affect the ratio? Now where they get that equation from, some of you said I couldn't find that equation. It's not on your formula sheet. Once again, being now that you can use a formula sheet, maybe this would be something you want to write down. But the idea of it is we take out all the variables that aren't changing. So the volume's not changing, the moles aren't changing, and R's not changing. It's just pressure and temperature. And then we set an equation of those variables on the same side equal to each other. So that's where we get, because I guess, so pressure is proportionate to temperature is what this is saying. And so then we move it aside, so we get P1 over T1 equals P2 over T2. Because that together will equal some constant value. Now once again, maybe you just want to write that down on your formula sheet since we can use it, and you can use whatever notes you want. so you don't have to figure that out yourself. The other options, it would be the same way. So let's just say hypothetically here for understanding. So let's say we had a problem where it was comparing volume and temperature. Okay, so in that case, I guess here's maybe a better way to think of it is move everything that's not changing to one side and then move what is changing to the other side. I don't know if that helps at all, but in a sense, so then we would have V over T equals NR over P. And we know since these aren't changing, they're going to be constant. And so then that's how you would get your equation. Honestly, this is probably the most common is pressure or temperature changes, but that's kind of where we get it from. And so then that's where we get the 299 over the 0.7 is equal to what the new pressure would be at 425, and then just solve for your pressure. Okay, so that's kind of where the equation comes from. It does come from Pervnert, rearranged a little bit. Once again, recommend just writing that down on your formula sheet just so you don't have to derive it in the time that's given. Okay, the way I know that I needed to use that was because of, we're talking about changing. Just Pervnert is if it's just under these conditions. So we're not changing the conditions, but under these conditions, we're finding a certain value. Okay? All right, C, in terms of the kinetic molecular theory, briefly explain why the pressure of CO2 in the container changes as it is heated. So really the main way, or the way I think about this problem is focusing on, oh, there's my other markers, what pressure is. That pressure is a measure of force per area. And so if you increase the force of the molecules, you increase the pressure. And so since the temperature went up, the speed of the molecules went up, they're hitting the walls of the container with more force, causing it to have a higher pressure. The other factor that affects pressure, so that was answering it in terms of force, so you got a point if you did it that way. The other one is area, which is frequency, so how often it's hitting. So if they're moving faster, they're also going to hit the walls more often, resulting in a higher pressure. So pressure can always be answered in two ways, either focusing on the force component or the area component. In this case, you only had to address one way, and you could have got the point. And then D, the student measures the actual pressure of the CO2 in the container at 425s and observes that it is less than the pressure predicted by the ideal gas law. Explain this observation. So let's just review where the ideal gas law fails. So the ideal gas law is based on the fact that the gas is behaving ideally, which means that it's not interacting with other things, like intermolecular forces aren't present, and things like that. And so, what was our original one? So originally we're at 299, and then the pressure was at 425, okay? Or the temperature, sorry. Sorry, I just lost my train of thought. So one of the main reasons why it is failing is because of the attractive forces. So once again, the intermolecular forces are actually causing these things to interact, when normally when something's a gas, it shouldn't. And so really whenever you have to justify a flaw in the ideal gas law equation, it's because of those attractive forces are causing issues. Yeah, and that's basically it. And it's kind of, that would be a common theme anytime the law is failing, is because of those attractive forces. Okay, there's question 4. Okay, let's talk question 5. Now, I know a lot of you in the comments said that question 5 seemed a little bit like a foreign language. You couldn't remember any of it. This goes way back to stuff we learned at the very beginning of the year. So if you were one of those people who said that, hopefully this will help. But then also might be a good idea to just go back and review electron configurations. Now, I can't guarantee anything because I don't know what it's going to be like, but being with the shortened version of the test and how they're staying away from memorization things, electron configurations might not be a big part of it because a lot of that you could just Google, at least in terms of writing an electron configuration of something. Now, interpreting a diagram, I could see because that would be a lot harder to look up. So the idea of these photoelectron spectrums, reviewing these, this is the idea of where using X-rays, you can take an atom, put it into the spectroscoper, and by sending X-rays into it, you can literally rip the electrons off each shell of your atom, okay? And then as they get ripped off, they get detected, okay? And so that's what these different peaks are representing. So the two things, X and Y axis. So the height of the peak represents how many electrons were in that orbital, and then the energy of the peak represents where it's located. The higher the binding energy, okay, so the higher the binding energy, the closer we are to the nucleus. Because the electrons that are close to the nucleus, right, these inner ones are held a lot tighter than the outer ones. So the one with the lowest energy would be the valence electrons. And then it goes in. So for writing a configuration, you start from the inside and work up, just building from the bottom of configuration patterns. Okay, so for configuration patterns, we always start with, sorry, I want my black marker, keep losing it. Okay, so this is for answering part 1. Okay, so the first peak here, this would correspond to the 1s peak, or the 1s orbital, and it can hold up to 2 electrons, which tells me this line means 2 electrons. We then go to the 2s peak, which also has 2 electrons in it. After 2s comes 2p. Now once again, if you're like, wait, where are these things coming from? Go back and review the pattern of electron configurations. Okay, the 2p can hold up to 6. Okay, and then goes 3s, 3p, and then 4s. Now the last one you gotta check because since it's a valence, it may not be filled all the way. In this case, it's the same height as the other s's, so it is. So that's where we get 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2 as our answer. Okay. For identifying that element, that once again goes back to the pattern of electron configurations and how they match up, and the 4s2 is really all you focus on. That corresponds to calcium. Okay. Part B says calculate the wavelength. Now once again, big fan, identify what is it you're trying to find. Focus on that so you know where to go. So it says calculate the wavelength in meters needed to remove the electron from the valence shell of the atom. Now if you look on your formula sheet, there are just 2 equations that relate to wavelength. And once again, we didn't use these a ton because the chances of it, even on the real test, it's only 1 question. But it's really easy once you have the equation. So there's 2 equations on your formula sheet. So the symbol for wavelength is this. Okay, once again, your formula sheet identifies that for you. So we have this equation, and then we have that equation. I guess, sorry, we only have 1 equation for wavelength. Okay, so this is what I'm trying to find. Okay, I don't have, so c is the speed of light, that's a constant. I do have that one, it's on the formula sheet, 3 times 10 to the 8th. I don't have frequency. The only thing I have is energy. So we have to kind of connect these 2 equations together, okay? So we have to use this equation to find frequency, and then we can use frequency to find wavelength. Now there is an equation once you rearrange it that already does that for you. So if you just rearrange it, you can see that energy equals hc over wavelength, which once again, this is derived by just connecting these two together through that common variable of frequency. Once again, since you have your formula sheet to use, this would be maybe a good one to write down on it as well, just as a quick reference if you need it, so you don't have to rearrange it yourself. And then if I rearrange this because I'm trying to find wavelength, so if I rearrange this, wavelength equals, whoops, wrong way, hc over E. Now, key things here, so once I get my equation, it's from the valence shell, so that's why we're using this energy. Okay, so that's where the energy comes from. H is a constant and C is a constant, and they're just defined for you on your formula sheet as well. So you would just plug those in. I don't think we even have to, nope, I don't think, do we do anything with our units? Because that's in joules. And speed of light's in meters, so yep, once you just plug that in, that's how you can get your answer. Okay, now once again, I know you have your notes and things available to you when you take the AP test, and so that should be a great comfort to you. But you also don't want to be flipping through a bunch of pages because it's a short time test. So have your formula sheet there, and as we go through this review month, maybe add little things to your formula sheet, and maybe if there's some other topics that you feel like, ooh, I could do this, but I really need this information, maybe make yourself a two-sided hint sheet that you can have when you take it as well. Still have your notes there, but once again, time can be a problem, and so having some quick reference sheets would make a big difference, and we can maybe talk about putting those together as a class if you feel like that would be useful. But okay, there's number 5. Okay, number 6. Okay, so number 6 gives us all this information and gives us these charts. And the first part says, explain how the graphs indicate that the reaction is second order. I don't see this being an actual question this year because you can just, once again, Google it, or you just have to have memorized it. But if you wanted to, it'd be a really simple thing you could write down once again on that, like, quick reference guide that I mentioned. Sorry, I keep looking out the window because there's some little kids doing weird things on the track. They're like running around like this, so it's distracting me. Okay, anyways, so the pattern is you're looking for the one that is linear, and the graph that is linear corresponds to a certain pattern. So 0 order reactions have a linear graph of just concentration. First order reactions have a linear graph of the natural log of the concentrations, or whatever the substance is, and then second order has a linear line of 1 over concentration. And so since our 1 over concentration is our linear line, that's why it's second order. Okay? Now, for writing the rate law, a decent number, and it happens every year, so you're not alone. Mixed up rate laws and equilibrium expressions. And I don't know why, maybe because they both have K's in them, but they're two totally separate things. And so let's just kind of review really quick. So equilibrium expressions is the products over the reactants. It shows you the ratio of a reaction at equilibrium. Once again, it only deals with equilibrium, and so first off, if a reaction is not at equilibrium, right, notice the single arrow here, equilibrium expressions don't exist for it. Rate laws are only based on the reactants, and they're helping you understand how quickly a reaction proceeds, so going from start to finish. The rate law, or the order of it, tells you the exponent in it. So the answer, so all rate laws have this same format. It's always rate equals K. The reactant, so in this case we only have one reactant, so it's NO2. And since we found it was second order, that's why we square it. Okay, so rate laws are only based on reactants. And to find this, we need experimental data, okay? All right, the second part of the problem then says, it gives us these mechanisms, and it wants to know if these mechanisms are consistent with the rate law you wrote in part B. So I'm gonna write that down just so we have it. So the rate law is K NO2 squared. So we talked about rate laws with graphs, you're looking for linear. Rate laws with mechanisms are all about the slow step. So when the slow step is first, you can just translate it into a rate law. So the rate would equal K, and you have NO2 and NO2, so NO2 squared. So yes, it does match. Justify your answer. Okay. For this one, when the slow step is second, you then have to substitute out things that are intermediate. So an intermediate is a substance and a mechanism. It's like a spectator, kind of, if you're connecting themes together, but it's something that gets made in one step and then used up in another. So this gets made, this gets used, it's an intermediate, and you can't have intermediates in a mechanism, and so you have to substitute it out. Well, since this one, this equals two of those, it's just a direct substitution, so that's why, yes, this mechanism also supports the rate law, because in a sense, the rate law would be this, which is going to be the same thing as this. Okay, so when the slow step is second, we have to kind of do some substituting out of the intermediate to see what it's equal to. So, okay, there's number 6. Yep, that was all of it. Okay, number 7, here we go. Before I do this last one, I just hope you all know that I miss seeing you. I do not just enjoy standing here in front of a camera and teaching to an empty classroom. I wish you were all here, even with all of your side comments and other things that happen. I miss it all. But here we are, and it is what it is, so we'll make the best of it. Okay, so part A is we want to identify the species that was reduced in the titration, and then justify in terms of oxidation numbers. So for this one, you need to know how to find oxidation numbers. Now, once again, with the format of the test changing, you don't have to have the rules memorized. So maybe oxidation rules might be another one that you want to put on that little help sheet outside of your formula sheet. Okay, but here we go. So oxidation numbers, if it's a single atom or ion, it is just the charge. Oxygen is -2, and then we have to do the math to find the manganese. So there's 4 of them, so that overall has a -8. It has a -8 charge, which means manganese would be +7 because these have to add up to the charge of it. Okay, in this one right here, so hydrogen is always +1, -2. So I'm writing the individual numbers on the top and totals underneath for the math. So this would be -8, this would be +2. It has to add up to 0. But there's 2 of those, so let's think. So total this needs to add up to is 6, which means individually they'd each be +3. Okay, oxygen is -2. There's 2 of them, -4, so that would be +4. -2 +1, and then +2. Okay, so reduction means that it is going down in oxidation numbers. So let's see here what went down, and it looks like my manganese did. So manganese got reduced. If the problem would have asked, carbon is what is being oxidized because it went up. Because reduction means you are, so think back to our little saying, oil rig. So oxidation is losing, reduction is gaining, and if you gain electrons, your charge goes down, okay? All right, there's A. Okay. B, the student uses a 50 milliliter burette to add the potassium permanganate to our other one until a faint lavender color has been observed, indicating the end point of our titration. The initial and final volumes are shown. Write the initial reading and final reading and use them to determine how much was added. Here's our picture. So pretty much for this one, you just take the starting point and subtract it from the ending point. I guess the biggest thing remembering is that you always measure from the bottom of the meniscus, as well as that burettes are numbered backwards. And so this is 29 and that's 30, so this would be a measurement of 25, probably, oh wait, that's 29, sorry. So 29, 1, 2, 3, 4, 5. So 29.55 is what I would say. I don't know what did they claim it to be? Oh, that's what they claim it to be too. So, and then you just subtract them from each other, okay? All right, C says, given that the concentration was that, calculate the moles of MnNO4. Now this was another problem that I kind of debated, but being that titrations is something that was like it's mentioned in earlier topics, not for unit. It's really heavy in unit 8 with acids and bases, but it's also mentioned. So the biggest thing to remember with the titration is that the equivalence point means the moles are equal. And so the moles of this are going to equal the moles of that. And so we have the concentration, we want to find the moles, and so since constant molarity is moles per liter, we just need to cancel out the liters with how much we added. And so that's what we got on part, the milliliters we got on part B, the 26.20, that's where it comes from. So biggest thing with titrations is that when you reach the equivalence point, the end point, the moles are equal. So the moles of this are going to equal the moles of that. So by finding how many moles of this we added, it's going to equal how many moles of that reacted. Okay? And then D, the student proposes to perform another titration, but this time using this concentration of potassium permanganate in the burette, so it's way, way, way more diluted. Would this titrant concentration be reasonable to use? And then to justify our choice. So let's look at what's changed. So we're still using, so this is the same. So we have the same amount of this, but we're using way less of that. And so the reason why it's not a good choice is because since you're using way less, you're going to empty your burette before you even get through the titration, which isn't very logical to do. So, yeah. Okay, there's number 7. So there's going to be a little form for you to fill out, kind of telling me some things that you learned, because it's good for you to reflect on that as well as any further questions that you had, okay? Please, 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 if I went through a problem but you still don't understand it, let me know. I'm not offended. If my first explanation didn't make sense, we can do it again. We can do it a different way. But the best way to help you review during this time is to not ignore the things that are still a little fuzzy. Let's get them clear as we keep going forward. Okay, see you guys later. Bye.